So hello everyone and welcome to this next lecture in the DC to DC converter lecture series. So I will continue in this lecture with the boost converter. So before I start this lecture, as always, a little bit of brief background that in case you are interested in this topic, that is of simulating power electronic circuits, but you find these video lectures to be a little too light, I have a complete comprehensive course on simulation using Python with my software Python Power Electronics, where I go through the entire process in a much greater detail. So if you are interested in this kind of work but you want something more comprehensive than these video lectures, by all means check out this course. The link for this course is provided in the description of this video, so just check out the description and you can check out you'll get the link. So to continue this lecture, in the previous lecture we had edited the parameters of the buck converter, or rather the boost converter, sorry. So now in this lecture, let's continue on with editing the control parameters. To begin with, let's go back and visit this circuit. Now in the case of a boost converter, we found that when the switch is open, right, the output voltage is 0, because in the buck converter, the switch is in series with the input. That is, the switch is somewhere here where the ammeter L1 is. So what this means is, in the buck converter, if the switch has no control and the switch is completely open, the output voltage is 0. In the boost converter, however, that's not the case. If you look at this circuit, the switch is here in this position in a parallel path. So if this switch S1 is open, there's no control. If I do not have any control, if it's open, then in that case, this voltage is connected to the output. So basically, the output voltage is at the same level as the input voltage, right? That's what happens in a boost converter when you do not provide any control to your switch, right? Of course, there is also a negative impact, that is, you do not want this inductor to be suddenly charging and things like that. So that's never a good idea. It's a good idea to actually provide some control to your switch. So let's go and jump start, because we already have some amount of work done with our buck converter and we can actually use some of it. So let me go and add the folder for the boost converter, because this one is the buck converter where I left off. So I'm going to add this folder. Maybe I just don't do it right. Okay. Okay, I had to add the folder. I tried to open the folder. Okay, so now I have two folders open. I have the buck converter and I have the boost converter, right? So what I'm going to do is I'm going to take this file getSignal.py. I'm going to copy it into boost converter. So let's do that. So let's go over to simulations. Let's go to the buck converter and take this file getSignal.py. All right. And while we are at it, we can actually also copy the descriptor, because we can just jump start a little. So let's go to boost converter and paste these two. Now let me go back to my simulator. Let's go back to the main page and let's go to edit control. Now here I'm going to add that getSignal.py. Alright, so I'm going to add this file getSignal.py. Just make sure that you're in the correct folder, that is boost converter. And I'm just going to give the description PWM, right? You can actually give a more detailed description you want, that's not a problem, but let's just save time here. And let's go to configure control. Now, as I said before, we already have we have exported it in the previous lectures with the buck converter, where I had exported the parameters of this getSignal, or rather the parameters of the getSignal.py. So these are the parameters, right? Now I could now use this to import it directly into this new file. So that way I save time. It's basically a saving time. So I'm just going to go here, make sure you're in the correct folder and choose getSignal._desk. So this is a descriptor. So I'm going to choose it. It's not done yet. You have only chosen it, right? It will only upload. You must click on this upload file button. So let's click on it and you see something happens. And now I have all the control inputs, right? So this is merely extracted the control inputs from the Excel sheet and populated into the database. So it's a very convenient way of doing it. So now we are ready to go with this lecture. Alright, you see we have everything we need. We have the control output configured, we have the static variables configured, we have time event variable, and we have the modulation signal, the carrier waveform, and the gate signal all stored for plotting purposes. So let's go and get started with this plot. Or rather, just have to go back to the main page. Go back to the main page, view output, and now let's click on the run button. Before that, let's go once to the circuit file and check out what it is we have. So let me close this file because this is the previous one, and let me open this one. Now in this case we had chosen a switching frequency of 10,000 Hertz, right? Let's keep it the same. The sampling time interval we had chosen to be 1 microsecond, right? And I guess it can continue to remain the same because PWM does need some fairly fine tuning. Our integration time step is 1 microsecond and our sampling time interval is also 1 microsecond. So basically we are sampling at every time instant when the simulation is actually being solved, right? When the equations are being solved, right? This is the same. We are just checking if the current time is greater than the actual simulation time clock is greater than the time event variable that we have stored. The time event variable starts with 0, so it should start right away. And they are generating the carrier signal. This is where we are adding this loop to the existing carrier signal to generate that sawtooth waveform, checking if it's greater than 1. Now here there was a change we made in the buck converter. We had assigned modulation signal to this global variable called open control modulation signal, which was generated in the control file. So we had generated this modulation signal as a gradually ramping up signal. Now this won't work because this has not been defined, right? So what we need to do, we need to comment this line and let's uncomment the previous line where we had given a constant modulation signal of 0.3. Alright, so let's do this. Now the next part is we're checking if the modulation signal is greater than 1, saturating it. This doesn't really, oh no, actually we are doing the comparison here. So we're checking if the modulation signal is greater than the carrier signal. If it is, then the switch is high. If not, the switch is low. So this is the firing pulse to the switch gate, or rather the gate pulse to the switch. And eventually we are saving these control variables so that we can plot them, and all this is pretty much can remain the same. So we are ready to go and run the simulation. So let's do that. We go back to our web browser. This is it. Let's click on run. It says simulation is running, but as always, please do go to the command line and check if there is an unexpected error. These unexpected errors are most important, especially when you have control files, because sometimes if you have a syntax error in your control file, those will not be picked up in the web browser, they will actually appear in the command line. For now, that's how it is. I hope to solve that soon. When that happens, I will post an update. Okay, so now that we have this, let's go add some plots. Most important plot we need to know is of course the output voltage. And we have this saved, I think it's from a previous one. Start the plot. We need voltmeter VO. Let's go back to our circuit and check once. It's actually the other file, this one. This is voltmeter VO with which we are measuring the output voltage. So we can just go back and say, yeah, that is indeed the case. Choose this to be VO, save the waveform. So the waveform has been saved. We click on done, the plot is generated. So now that we have this, let's click on it. And we have a plot. Actually, I need the file browser. And this is the output voltage. So we have an output voltage which is between 15 and 20. So it's like around 17. So let's go back to our circuit parameters and check out what kind of a voltage we have provided. Alright, let's go all the way down, and here's our voltage source. So we have a DC offset of 12 volts. What that means is our DC voltage has a value of 12 volts. The voltage magnitude is 12 volts. It's like basically a battery. It's like a car battery. And the output is around 70, right? So now let's go back and do a little bit of calculation. According to the theory of boost converters, what we expect as the output is the input voltage divided by 1 minus the modulation signal or the duty ratio. The duty ratio we have chosen to be 0.3, right? We have chosen this to be 0.3, it's a constant. So that means this is what we expect. And if you press enter, you get a value of 17.14, right? So this is the output voltage you would expect. The output voltage is greater than the input voltage because it's a buck boost converter. And let's go back to our figure and you see, yes, the output voltage is indeed around 17 volts, right? So the simulation is correct, right? Now that we have done this, let me just delete this. Oops, just save this and let me go back and let me add a few more plots. And of course, one of the main plots we need to know is inductor current. Start the plot. We need ammeter L1. Let's call this IL. Let's give it capital L because that looks like a 1. Save it. Add another plot. Let's call this, actually we don't need, do we need, what else do we need? Let's have the diode current. Actually there was one mistake. We have not plotted the switch current, right? We have not plotted the switch current, we should have, but I would say you can use that as an exercise. Try it out on your own. Ammeter diode, call this ID. Save the waveform, done. And let's plot these two together. So I'll just say IL, save the waveform, the inductor current has been plotted, ID, save the waveform, and they both can have the same scale because they're both currents. There's no need to actually scale one with respect to the other. And we can stop this. So let's start clicking some of them, right? So let's click on the inductor current plot. Most probably we'll have to do a zoom because it'll be way too fine. Yeah, and expected it is, we need to do a zoom. So let's just choose a point, let's say 0.5 to 0.501. Seems fine enough. And now you have it, alright. So you can see this is the boost converter working in continuous current mode. The current never goes anywhere near 0. The current charges when the switch is on. Let's go back to the circuit and see when this switch is turned on. This is when the voltage source now charges the inductor through this switch, alright, because remember the current will always flow through the path of least resistance. This forward path is not the path of least resistance because there is a capacitor here, right? This switch is the path of least resistance because it's almost a short circuit. So that's why the inductor current will rise when the switch is turned on. And when the switch is turned off, that is when the voltage source will now, voltage source and the inductor charge the output capacitor through the diode. That's when the inductor voltage falls. Why? Because it is now facing opposition from the capacitor voltage. That's what's happening. So let's go and plot. Now I'll go back to the web browser and plot the diode current for the same range. And this is the diode current. So as you can see, the diode current only flows when the current is falling. If you see from before, well actually I should probably zoom in on this. In the previous case, we saw that the inductor current was rising and was falling. So there was like a kind of rise and fall. and you see that when the inductor current was rising, the diode current is 0 because the diode current is not conducting, and the reason is because the current through the inductor is flowing through the switch, right? And since this output voltage is greater than the input voltage, because remember this is a boost converter, the output voltage is greater, the diode is reverse biased because there is a greater voltage on the cathode than on the anode. The result is the diode is reverse biased and it cannot conduct a current. So the capacitor cannot discharge through the switch through the diode. The diode is reverse biased. It will not let the current flow. So this is why you have current flowing only when the current is falling through the inductor, right? Now let's go and plot the last one, which will be an interesting plot, and that is the inductor and the diode. So the same range, and let's plot it. And we can just check, yeah, this is the inductor and diode current, and this is a nice plot, as I said. So this, you see there are two lines here. The blue line is the inductor current, and of course there are times when it tends to disappear. The reason is not really it's disappearing, it's just that they are two superimposed, right? And the orange line is the diode current, which we just saw. So you see, when the inductor current, the blue line, is rising, that's when the inductor current is rising. And when the inductor current is rising, the diode current is 0 because the inductor current is now flowing through the switch. And as I said, I would strongly advise you to go and add an ammeter in the switch so that you can add a third plot and compare the inductor current with the switch current, right? I will leave that to you as an exercise. Now, when the switch is turned off, the inductor freewheels through the diode. That's why you see the blue line disappears, because the blue line and the orange line are superimposed, right? So this is when the inductor current is equal to the diode current and they are both flowing and charging the capacitor. This is the reason why both the input voltage and the inductor are now charging the output capacitor, and this is why the output capacitor has a voltage that is higher than the input voltage. This is the concept of a boost converter, right? So with this, I think I can end this lecture. There are several other plots that you can generate, and I'm sure I would strongly advise you to go ahead and check out some other plots. For example, you can always check out the plot of the capacitor versus the inductor. Well, actually we can do that too. Let's add that plot. Inductor and capacitor current. Already we have saved it from before. And yeah, this is a capacitor because this is the ammeter Cout is the ammeter in the capacitor branch. So that is what we want. So that's good enough. Save this waveform. And next, inductor current. Save the waveform. They both can have the same scale, so no problem. And save it. So now we've created a plot where we are comparing the capacitor current, or the current through the capacitive branch, with the inductor current. So again, let's give that range of 0.5 to 0.501. You're welcome to choose another range. And it should be done. Let's go. And you see we have plotted it. So now you see this is the plot which shows you exactly what's happening. Now here you will see that it is slightly different, and the reason why it's slightly different is because there is a time when the inductor and the capacitor are not at all connected, and there is a time when the output voltage, or rather the capacitor voltage, is also charging, or rather it is discharging through the load. So this is the reason why you do not actually see the same impact as you see with respect to the inductor voltage. To get a better idea, let me just quickly delete this plot and create another plot where we'll add also the load current. So let me just go and let me add this load ammeter as well. So I'll just call this filtered currents, just to give you an idea that I'm adding 3 of them. This can be added as usual. Save the waveform. add the inductor current, save the waveform, and finally add the load current. So I'll just call it load. And they can all have the same scale, no problem. So we have now 3 waveforms in the same plot. Click on done, come all the way here, and let's plot it for the same range. And let's plot it. And this is what we get, filtered currents. Let me look for that. Yeah, this is the one. So this is a line. Of course, there is, I believe, a slight mistake. I think we reverse the polarity of the ammeter, the load ammeter. So you see what's happening here. The blue line is the capacitor current, the orange line is the inductor current, and the green line is the load current. Now, the load current is not really negative, right? The reason why it's like this is because we actually have provided the wrong polarity of the ammeter. The ammeter should have been reversed. But anyway, I would again leave that as an exercise. By all means, go ahead and do it. So you see here, the load current is absolutely steady, right? It's the capacitor current that contains the ripple in the inductor. You see, this is what is happening. The ripple in the current in this capacitor is bipolar. The reason why it's bipolar is because there is a time when the capacitor is not connected to the input. At this time, the capacitor is discharging through the load. And there is a time when the capacitor is connected to the input, so the capacitor is being charged. So there is a time when the capacitor is being charged, and there is a time when the capacitor is discharging, right? So for example, this is the time when the capacitor is being charged. And you will see that this is indeed the case because this is when, or rather it's the other way around, this is when the capacitor is charged. For example, when the inductor current is rising, the switch is closed, the diode is not conducting. This is when the capacitor is discharging through the load, right? And you see that it's almost constant. The reason is because the capacitor voltage is almost constant. We've chosen a large DC capacitor whose voltage is retained even though it supplies a current to the load. So that's why the current is almost constant, because the load is constant and the capacitor voltage is almost constant. There will be a slight change, but very slight. It is the other time, that is when the capacitor is charging. So this is when the current reverses through the capacitor. And you will see that the current in the inductor will be the same as the current through the capacitor. Alright, almost the same, because now you see the capacitor is, even during this period of time, also discharging through the load, because the inductor current flows partly through the capacitor and partly through the load. This is the reason why you will see that there is a difference in magnitude between the inductor current and the capacitor current, because the remaining part is flowing through the load. Right? And you see the load current is very smooth. The reason is because the output voltage across the capacitor is fairly smooth, because we've chosen a large DC capacitor that has a filtering effect. And the result is that if we were to choose, actually if you were to reverse the polarity, you will see that this is a much more filtered version of the inductor current. So the moral is, eventually the conclusion is, the ripple in the inductor current is flowing through the capacitor, which in the end results in a smooth current flowing through the load. This is the filtering effect of the capacitor, right? So with this, I will end this lecture. As before, this does not stop here. You are very welcome. If you've been following along, you are very welcome to add several more plots and play around with them. However, I will, at this point, of course, you can also play around with the plots where we are generating the control signals. I have not done it because they are identical to the buck converter case, but you are welcome to check them out. So if you have any doubts, please do post in the comment section. Otherwise, I will end this lecture and I will see you in the next lecture, where we will, as before with the buck converter, go very briefly into an open loop control strategy for the boost converter, where we will gradually ramp up the DC, or rather the duty ratio, from 0 to a constant value. So once again, I will end this lecture. See you soon in the next lecture. Thank you so much and goodbye for now.